Hi, I'm Angelle Tanner. I'm an associate professor. I'm still getting used to saying that at Mississippi State University. I got my undergrad degree from Arizona, grad school UCLA, and I've been doing various extrasolar planet projects ever since. Most astronomers tend to focus on one aspect, just the way my career's gone. I've kind of thought about lots of different ways of detecting extrasolar planets. I haven't detected any yet, but I know what to do and what not to do. I need to start not using my title so much. It's kind of the title I use whenever I don't want to think about doing a clever title. But yeah, we are looking for Earth 2.0. We have lots of different methods that we're using to do that. Your definition of Earth 2.0 may be different than mine, and that's part of the discussion that the astronomers are having right now. So as of when I had to send the slides in, you can even tell it was the due date, as of October 10th, or October 1st, we've discovered, I just now rounded, over 3,000 different extrasolar planets. And this website, which is kind of nice if you want to play with extrasolar planet statistics, is called exoplanets.org, and it's fairly user-friendly. I get pretty impatient whenever I play with these types of plots. But the blue dots, those are going to be the radial velocity planets, the ones that were some of the first planets that were discovered. I know pulsars were kind of the first planets that were discovered, but not really, because there was a radial velocity planet that was published in 1989. So the radial velocity planets are here. The red guys, as you can imagine, are all the Kepler planets that were found during the Kepler mission using the transiting method. There are a few brownish ones here. Those are the directly imaged planets. And some green guys hanging out in here are the microlensing planets. And of course, this is a plot of planet mass versus separation in astronomical units, and planet mass and Jupiter masses. So some of these are not necessarily natural differences in the populations of the planets. There is an observational bias that's involved in all the different detection methods. I'm sure you are very aware of the fact that we define the habitable zone when looking for planets naively a little bit as the area where we think liquid water can exist on the surface of the planet. The Earth is in the middle of the habitable zone, Venus is on the inner edge of the zone, and Mars is on the outer edge of the zone. And this location and width of the habitable zone changes with the type, the temperature and or mass of the star, of the host star. So that's also something to consider. That's why you keep hearing whenever we're looking for planets around M dwarfs that they're going to be very close to their host star and have orbital periods of weeks to days even. And then this particular diagram is showing you that we've actually found a few planets in the habitable zones of their host stars. Are they exactly like Earth? We're not sure yet. Who knows? Because the masses are not quite perfectly that of the Earth. Okay. So as far as that plot that I showed at first, where we really need to start finding planets are down here at this mass. Earth has a mass of around here, and over here at this distance. And you can tell that our planet detection methods aren't quite diving into this sweet spot yet. But with all the new technology that's coming up and the new techniques and the new missions, this is what we're trying to fill in. So a lot of people have talked about the Proxima Centauri planet. Sure enough, the closest star to us besides the sun. I always trick my students when I do that. They get it wrong half the time. What's the closest star to the Earth? Oh, it's Proxima. The Proxima planet was indeed found using the radial velocity method. Gilliam did actually go into archival data and combine it with his own data. I'll tell you that there's rumors that he thinks there may be another planet in the system, but it hasn't been published yet. And sure enough, the Proxima planet is in the habitable zone of Proxima. And Proxima is an M dwarf, not even visible to the naked eye, actually. No M dwarfs are visible to the naked eye. So while we're excited, it's not going to be life as we know it on this planet because the planet's orbiting an M dwarf. So it's going to be sort of interesting. Another one that almost is a lot like the Earth is Kepler 186f. Now, of course, it's really far away, as most of the Kepler planets are, but it has a mass of 1.1 times the mass of the Earth. and it's in its habitable zone, roughly on the outer edge, but it also orbits an M-dwarf. So that habitable zone is a lot closer to its star than the Earth, and it has a period of 130 days. So the TRAPPIST planets, of course, made the news. Turns out I actually observed the TRAPPIST system looking for planets, but the precision on the telescope that I was using wasn't even close enough to detect these planets. These planets were actually originally detected using the transit method, and I wasn't using a transit method. But now we have a whole set of planets. Everybody's excited. They all have various masses, hovering around plus or minus the mass of the Earth. They're all in the habitable zone. And I can tell you that I have on my laptop right now, people are already thinking about the spectra, trying to collect spectra of the atmospheres of some of these planets using JWST. I was getting a lot of slides or a lot of emails the past couple days where they've been fiddling with their models to get the spectra of the atmospheres. So what's it going to take to find Earth 2.0? This is the radial velocity method. I mentioned before, it's where we found some of the first extrasolar planets, the famous one being 51 Peg. In case you want to know, the precision we're going to need to detect one Earth mass planet around a star like the Sun in the habitable zone is about 0.1 meters per second. If I wanted to look for an Earth mass planet in the habitable zone of an M-dwarf, then I'd have to have a precision of 2 to 7 meters per second. So how are we doing right now? Oops. So right now, at the optical, our state-of-the-art is about 1 meter per second. And I know that new instruments are being developed, like Espresso on the VLT, and I think they're kind of convincing me that if they keep doing it the way they're going, they're going to be able to reach the precisions needed to detect Earths. Right now, in the infrared, we have precisions of about 5 meters per second. I know that some of the work with some of the teams that I'm working on, he just said it on Twitter, so it must have been true today, that we're reaching precisions of about 3 meters per second with an instrument that we're playing with called iShell on the IRTF. So we're approaching the precisions necessary to find these planets. I think instrumentation-wise, we're going to get there. The problem is that the stars can be very active themselves, especially the M-dwarfs. They have lots of flares and star spots. So we're also working on how to mitigate that effect or choose the targets that are going to be the least problem. This is the transit method. I like my little NASA. We pay good money for these cute little animations. So if you're thinking about trying to find planets with the transit method, you need to reach a photometric precision of about 100 parts per million to see a planet which is the size of the Earth going around a G-star. And of course, Kepler, that's what Kepler was designed to do. So Kepler had reached that precision, and sure enough, it's found a whole host of planets which are about the size of the Earth. And it's also doing statistics. It's basically a census taker too. It's really exploded our knowledge of extrasolar planets. The problem with Kepler targets is that they're very far away. Some of them are nearby, and those have been followed up with the radial velocity method. But a lot of them are 1,000 light years away, and it means their host stars are actually too faint to follow up with ground-based technology. So we're excited with our new instruments to be able to try to follow up those targets. TESS is very exciting. They're getting to it. They're getting nervous. I can tell in the sound of their voice when they're talking on telecons. The Transiting Extrasolar Planet Survey satellite was started by the MIT. This is one of the first satellites that the main people running it. It's a NASA program, but the main people running it's actually a university. So it's going to launch in March 2018. It's going to be nice because it's going to be an all-sky survey, and they're going to target a bunch of really bright stars. So some of the stars are even going to be visible to the naked eye and binoculars, and obviously with the types of telescopes we currently have. That means I have 10 minutes left? Oh, cool. All right. So we're excited about that because we're even, some of you, if you're any amateur astronomers, if you have friends who are amateur astronomers, you might be able to use your backyard telescopes to provide data to support the TESS program. So we're very excited about that. And it is going to be all sky. And so a lot of these stars are going to be in our backyard. And we think that a lot of these planetary systems we're going to find around TESS targets are going to be ideal for follow-up. So we already have Proxima and TRAPPIST ready for JWST, and then TESS is going to find us a whole bunch of stars to follow up with JWST and the other missions. It's been talked about here, but What's nice about the transiting planets is we can sample the atmosphere of the planet, because as the planet goes in front of the star, this is not to scale, there's a little thin layer of atmosphere around the planet, and we can use, and some people just got clever with the math and realize that if you observe it while it's not in front and while it's in front and you do some math, you can end up with you can measure the radius of the planet at different wavelengths and get a spectrum of the atmosphere of the planet. You can also get a spectrum by doing special math of the planet before it goes behind the star as well. So that's transiting spectroscopy versus thermal spectroscopy. And these two methods actually, they sample different parts of the atmosphere, and they sample different types of the atmosphere, because this is transiting, this is transmission, and this is thermal. So it's also sampling different physics too. We'll be studying the atmospheres of Earth mass planets for some of these ones that we find with tests, but it's going to have to be the ones that are around the M dwarfs, at least with ground-based missions, because of the signal to noise we need and just the way the physics works out. So we're still pushing with the 30-meter telescope, which we think is going to be in Hawaii. It's still set for 2022. The giant Magellan telescope set for 2021, and the Europeans with their extremely large telescope is set for 2024. So we can definitely follow up some of the Earth mass planets around the M dwarfs with these ground-based facilities. And then JW, of course, being in space, it will do a very nice job of getting some of these guys too. But it's not going to be able to really do an Earth mass planet in the habitable zone of a sun-like star. It's going to also have to focus on the M dwarfs. And in case you haven't heard, the launch date got put back just a little bit. Now all the astronomers are like, because apparently right now, this is getting real. Blank's getting real now, because this thing's about to launch. So they're already soliciting proposals, and some of my friends on the internet were like, well, does that mean that our due dates for the proposal gets pushed back? And apparently not. No, they still have to turn the proposals. So they were hoping for extra time to write their proposals. We've had 20 years. We should have our act together by now. But in this case, this is a model of using NIRSpec on JW and looking to find CO2 in the atmosphere of a transiting planet that's got a radius of 2.3 times that of the Earth. So, we'll definitely be able to find biomarkers with JW. Direct detection, there's our little thing. If you wanted to directly detect a planet around a star with direct imaging, we have to use something called a coronagraph. And if you're looking for an Earth mass planet 10 parsecs away, it's going to be 1 billion times fainter. So it's not, the problem isn't getting the photons from the planet. We can do that if we leave the shutter open for a long enough time. The problem is the star. We have to use this coronagraph to block out the light from the star. Otherwise, everything just gets too noisy. And this is the example of that. This is using the Gemini Planet Imager on Gemini South. And this is their little planet that they found. And you can see this, that's Photoshop. But the rest of these are not planets. This is noise. And so the coronagraph takes care of some of the light, but it doesn't take care of all of the light. And these speckles, as I can appreciate, they tend to mimic planets. So you have to use some special math and special techniques to try to reduce this noise, and we figured that out. And then also, you can't just assume that's going to be a planet. You can't assume that planet's bound to that star. You actually have to either get colors of the object, or you have to wait for the star to move over in a couple months and take the image again and hope that this guy follows along. Mother Nature has fooled me multiple times. Thank you. And we're going to have to realize that whenever we're looking at Earth mass planets, we're looking at reflected light. The Earth doesn't produce that much light, especially in the optical, on its own. Take away the sun, we're pretty dark. So it's going to have to use reflected light. And based on our calculations, we're not quite there yet, especially from the ground. Even using adaptive optics on an extremely large telescope from the ground, we can't do it to detect an Earth around a sun-like star. So we're going to have to go into outer space. And obviously, if you take a picture of the planet, you can put a prism in the field of view, and you can get the spectrum of the planet here too. But we're going to have to use specialized missions to do this, and there's a lot going around. I've heard Other Worlds Imager, HabEx, WFIRST is involved, and possibly using this weird-shaped flower-like coronagraphic machine to block out the light. And it's kind of cool because the shape, the little petals here, it's just good math. It blocks out the light without too much stray light. And this is a simulation of what these guys might be able to do for an Earth-like system. Yeah, here's more stuff. And if we want to use an interferometer, I know JPL has been working on free-floating instruments, or free-floating spacecrafts for a while. And of course, you're going to have to account what type of star your planet's orbiting around, and we talked about a little bit more in the biomarkers panel. You have to think about all the chemistry and geology and all that stuff if you're going to believe it's life. There's more spectra, theoretical spectra. And then it's sort of been talked about a little bit. We could build a really, really, really big telescope and put it in outer space and actually take a picture of these planets. But well, a lot of the engineering that's been going on so far, we haven't even thought of how to do it completely yet. So maybe we'll figure out how to do this in the future too. I think that's all I have to say. Thanks. Cool. What?
Just curious, the fact that they found several planets or many planets around Proxima Centauri and none around Alpha Centauri, does that imply, of course maybe we're just bad at looking, but on the other hand, does that imply that double stars just have a problem with stable orbits for planets?
That is totally something that we look into, is how close can the companion be to actually form planetary systems. And you do have to worry about it. And I don't think we've really found enough systems in binary systems, or enough planets in binary systems to get the statistics to understand that completely. I can tell you that they're definitely monitoring Alpha Centauri a lot. There are instruments, Deborah Fisher, she has an instrument in Chile where that's all they look at is Alpha Centauri. And a lot of it, again, has to do with dealing with the activity of the star itself, too. But you're right, it is kind of weird that we found Proxima, but not any planets around Alpha Centauri yet. Yeah.
So Mark Weber from Washington State University. This may be a trivial question, but are there any models of what kind of size distribution of planets you do expect, or?
Oh, yeah.
Okay.
Yeah, thank you. I didn't include it. Okay. Definitely with Kepler, the big plot that they're using is radius versus mass, which is basically density. And all the theorists gave us beautiful little curves, so it looks kind of like this. And you can tell if you've got a water world or a lava world or a rocky world or whatever, or a sub-Neptune, because they're kind of fighting about whether or not a sub-Neptune is really a rocky planet, because it's not. And the dots from Kepler are all over the place. So there's definitely not really been a trend. We have a huge variety in the density of the planets that we're finding. And again, the Sarah Seegers of the world are doing lots of work to try to figure all that out. It's kind of cool. Definitely a menagerie. I have to stop because it says stop. All right, thank you. Next speaker.